All right, so exponential decay sounds very uplifting, but exponential decay is really just what it sounds. Exponential means that we're going to have something that curves, something that is a result of repeated multiplication, and decay means that we are losing or that something is decreasing in some way. So in lesson 512, you found that the relationship between the height from which the ball is dropped and its rebound height maintains a, let's say, semi-constant ratio. And that's really because the numbers are so small. In this lesson, you'll continue this investigation by exploring the mathematical relationship between how many times a ball has bounced and the height of each bounce. So if we, hold a ball up and we let it go and it only bounces once, we would measure the bounce height. But what if we measure the second bounce height or the third bounce height and not touch it in between? So what we did originally was we found the rebound ratio for a ball, and the sample data that we had said that the ratio was 0.74. Did the height you dropped the ball from affect the ratio? And we said, yes, there was some difference. Some were higher. Yes. That some were higher and some were lower. I'm not sure why I got so excited about writing yes. If you were to use the same ball again and drop it from any height, could you predict its rebound height? And we would say no, because the ratio wasn't consistent, but it was pretty close. We would say the ratio was not totally consistent. We were getting other numbers besides 0.74. But pretty close. And it was pretty close for the data set that we were using. If you looked at the video check-in for 512, you notice that when somebody performed the ball bouncing significantly further to the right on the axis, much, much larger X values, that all of a sudden the data showed that it did in fact start to curve. A model for many bounces. Imagine that you drop the ball you used in problem 519 from a height of 200 centimeters, but this time you just let it bounce. Predict your ball's rebound height after each of the 6 successive bounces if its starting height is 200 centimeters. So when no bounces have happened, you're at 200 centimeters. After one bounce, you would have kept 0.74 of your height. So if you take a look on my calculator, what I do here is I can do 200 times 0.74. And I would say if I kept 74 hundredths or 74% of my bounce height, I would go down to 148. Well, what happens if I don't stop the ball, right? So now it tops out at 148 and it starts its second bounce, 148 times 0.74. Now I'm only getting back up to 109.52. Well, now that's my maximum height. Now it starts on its third bounce times 0.74. And I think you can see sort of the pattern where its maximum height is getting shorter each time because I'm only getting 0.74, 59.97. Let's go with that. Let's round it. I'm going to leave the full number on my calculator screen times 0.74, approximately 44.4, and then times 0.74 again, approximately 32.8. Now, what does that mean? Every time it bounces a little lower, a little lower, a little lower. We know that each time it bounces, it's losing some of its energy when it hits the floor. And the reality is it actually going to continue to bounce forever? No. We know there's going to come a time physically in the real world where it's going to stop bouncing, but mathematically, it will always continue to have 74% of its bounce if we don't have any other factors. The independent variable was the bounce height, and the dependent variable was the rebound height, and that came from our X and our Y axis on the previous graph. Graph your predicted rebound heights on the grid provided. So if you look at the second page, what I've done here is I've graphed after 0 bounces, 1 bounce, 2 bounce, all the way up to the 6th bounce, and you can really see that curve. You can see that it's going down, but it's not going down in a straight line. It's going down in a curved pattern. And it says, should your graph be discrete or continuous? So my question to you is, can you have 1.5 bounces? And the answer is no. We are counting bounce number 1, bounce number 2, bounce number 3 as our x-axis for this one. So this is going to be discrete because we are counting and not measuring the number of bounces. We can't have 1.5 bounces. Or we can also say because we are counting, not measuring. A function can be used to model the data from problem 529. Compare your graph for the height of successive bounces in problem 529 to the graph of drop height versus bounce height from 512. Can you make the same kind of equation? And we would look at this and go, obviously not, Mrs. Fraser. A, it's a curve. B, it's clearly not going through 0, 0. So things that we can't do, we can say, nope, it's not linear. So we cannot use y equals mx plus b. This is a form of exponential decay. Exponential meaning curved. And we can also say we know that it's not going through 0, 0, which is kind of an afterthought. It's already not linear, but just we know it's not going to match the equation from the previous one because it's also not going through 0, 0. Describe how the pattern of growth for successive bounces, meaning one after the other, how is that the same or different from other models you've looked at previously? So what's really happening here is that each bounce is based on the previous bounce. They're not independent of each other. So each successive bounce is based on the previous one. And this is a pattern of repeated multiplication. And that's what makes it curved and not linear. If you continue to let your ball bounce uninterrupted, how high would the ball bounce after the 12th bounce? Now, this is really cool. We started with 200. Our initial value is 200. And then you're going to take the number of bounces as your exponent, right? So 12 bounces. And then the number that goes in here is whatever your rebound ratio was. So we might represent that with an R, but for our actual equation, we would say 200 times 0.74 to the 12. So 200 is your initial value. I crossed the wrong one here. That's where initial, I-N-I-T-I-A-L, initial value. This is your rebound ratio, and this is your number of bounces. So we could do this for anything. You could do this if you had performed one at home and you found something that had a different rebound ratio and you wanted to predict, after 6 bounces, and the one that I was doing had a starting height of, 100. You could figure out what your 12th, 6th, whatever bounce would look like. Would your ball ever stop bouncing? In reality, yes. Mathematically, based on our equation, no, it'll go on forever. So in reality, we have all kinds of other scientific factors. It will stop. According to our graph / equation, it will go on forever. All right, so exponential decay basically wrapped up is saying that it is decreasing, that you are in some way, shape, or form losing. In this case, I'm losing height, and that it is a curved pattern. So that's the general gist of it, and I'll see you guys in class.